Hello and welcome to the Radeon GPU Profiler update. This video describes the changes and improvements made to the Radeon GPU Profiler during updates 1.9 and 1.10. It focuses on the new features recently added to the Radeon GPU Profiler, or as we like to call it for short, RGP. RGP version 1.10 includes support for the AMD Radeon RX 6000 series of GPUs, which are based on the RDNA 2 architecture. The API and operating system support remains the same as in previous versions. A new cache counters feature allows you to view the cache hit data for instruction, scalar, L0, L1 and L2 caches. The cache counter data is displayed in a new swim lane in RGP's wavefront occupancy view. This feature is also supported on the earlier AMD Radeon RX 5000 series GPUs. RGP now supports DirectX and Vulkan ray tracing workloads, displaying the new API events and the subsequent GPU activity as additional data fields within the existing RGP UIs. Let's take a deeper look at these new features. To include cache counters in your RGP profile, you must enable the Collect Memory Cache Counters toggle in RDP's Profile tab. After you select this option, the subsequent profiles will contain the additional cache counter data. In RGP, the cache counter data is displayed in the wavefront occupancy view, in between the occupancy graph at the top and the events view at the bottom. The counter data is displayed on the same timeline, making it possible to correlate with other activity on the GPU. Mousing over the counter view displays a pop-up summary of the hit data at the mouse position. The summary displays more detailed data at the position of the mouse, including the hit percentage, the number of requests, hits and misses. The list of counters and their values are ordered based on the cache hit percentage, with the highest at the top. As the mouse is moved along the graph, the list updates with the values and then reorders the rows based on the new percentages. As with other RGP views, the cache counters can be displayed in a variety of ways to help you understand the behavior of your application. Just above the cache counter graph is a pull-down to select which counters are displayed. Using this control, I can focus on just the L1 and L2 cache. In the color key under the cache counter graph, each of the counter color boxes can be toggled to shade the area under each of the graphs. Here we see the result for L2 and L1. With the addition of cache counter data, it is possible to answer key performance questions that were not previously possible with RGP. For example, one cause for high wavefront occupancy accompanied by low performance is when wavefronts are competing for memory access. This scenario can result in cache thrashing, and we would expect to see lower cache hit values being displayed. Conversely, low-performing regions of high wavefront occupancy, where cache hit rates are high, might point to other issues such as serial dependencies within the shader. One of the key usage cases for cache counters is to understand how shaders behave in terms of locality of memory access. A low-performing shader with low cache hit and a high number of requests may be an opportunity to optimize the memory access pattern. The behavior of the different levels of caches can indicate the scope of the access pattern change that needs to be analyzed and optimized. Here we can see the memory hierarchy used in the RDNA 2 cache architecture. Within each workgroup processor, 2 L0 caches are used, one for each of the 2 compute units. The L1 cache serves all workgroup processors in a shader array, and the L2 cache serves all the shader engines. To find out more about how to optimize your shaders for the RDNA architecture, check out the Optimizing for the Radeon RDNA Architecture video on GPU Open. Next, let's take a look at the ray tracing support that has been recently added to RGP. New API events have been added to RGP to support ray tracing workloads, 4 to support DirectX and 9 for Vulkan. In RGP, ray tracing events are just like the existing graphics and compute events in that they are created using an API and result in GPU activity. As such, ray tracing events fit nicely into many of the existing RGP UIs. Let's take a look at the various RGP UIs and see how these new events have been integrated. So you're probably wondering what the new red regions of activity in the wavefront activity graph are. Just under the graph, a red ray tracing stage has been added to the color key to represent the occupancy of ray tracing related events. In this view, the dispatch rays event, number 1235, has been selected in the event timeline. On the right-hand side, in the event details pane at the top, we can see the selected ray tracing events, call name and arguments. There's a new API shader stage entry in the ray tracing shader statistics table and a new ray tracing stage in the workload shader stage below. Let's take a look at some of the ray tracing events in more detail. Zooming into the ray tracing events at the beginning of the frame, we can see some user markers in the overlay at the top of the events view. Mousing over them, we can see from the pop-up that we have multiple user markers for the Build Ray Tracing Acceleration Structure API call. The Radeon driver has inserted these user markers automatically. Looking below these, we can see how the Build Ray Tracing Acceleration Structure API call results in several internally generated command dispatch build BVH calls, each of which corresponds to one compute dispatch among the several that constitute the DX command call. Let's move on to see how ray tracing events appear in RGP's overview windows. Starting with the most expensive events overview, a new ray tracing stage has been added to each event in the list and is rendered red when active. The Render Depth Targets overview displays the ray tracing events in the Other category, along with the compute events, again rendered in red. The ray tracing passes are also clearly labelled at the top of the graph. Similarly, in the Pipelines overview, a new ray tracing stage has been added to the Pipelines list. Also, at the top of the UI, a ray tracing summary count has also been added. Let's dig into the ray tracing related changes in the events window. We still have event 1235 selected and can switch to it in the event timing view. Not much has changed in this view, but we are now able to use the color by drop-down to color by ray trace. The event details pane on the right hand side is the same one as used in the wavefront occupancy, which we've already covered. Before showing the pipeline state for the dispatch raise event, I should explain that currently there are two compilation modes, and these are chosen by the driver and compiler. For dispatch raise compiled with unified mode, the individual shaders are inlined into a single shader, resulting in a single stream of ISA. For dispatch raise compiled with indirect mode, the individual shaders are compiled separately, and the functions in each shader end up as their own stream of ISA instructions. The pipeline state view for dispatch raise, compiled using the unified mode, looks like any other compute dispatch event. However, for dispatch raise compiled using indirect mode, the UI has significantly changed. There is a new shader table tab that contains an interactive visual representation of the ray tracing pipeline, as well as a table listing all of the shader functions referenced by the selected event. The table gives information about each shader function. In this view, the ray tracing flowchart indicates the relative cost of each stage in the ray tracing pipeline, as displayed by the red, orange, and green percentage bars in each stage. Any enabled stage in the flowchart can be clicked and will filter the table below by that shader type. More than one stage can be selected by using Control mouse click. You can also filter the table by using the Show Filters drop-down. From the shader function table below, you can click on one of the hyperlinks to view that shader function in the ISA tab. The ISA tab can also display the ISA from the other indirect shader functions. by using the drop-down selector to switch between them. This will also update the shader statistics table just above the ISA display. The instruction timing view has also been updated to support the indirect ray tracing shader functions. This view displays the disassembled ISA code from all indirect shaders, which have a non-zero hit count. This example shows a dispatch raise event. There is an additional export name drop-down at the top of the view, allowing you to navigate to the ISA of a particular shader function. This drop-down contains a list of all indirect shaders sorted by the relative cost of each shader. When selecting an item from this drop-down, the disassembled shader code will scroll to the beginning of that selected shader. This allows you to quickly see the instruction timing data for any given indirect shader. The instruction types table in the details panel also includes a new row displaying the hit count of the instructions. Here we can see the ray trace hit count is 38,839. Looking at the ISA code, we can see that the selected event has an image BVH64 intersect ray instruction with the same hit count value. Here's a quick review of the new features introduced in this version of RGP. And that about wraps it up for this version of the RGP update. The Radeon GPU Profiler is now part of the Radeon Developer Tool Suite and can be downloaded directly from GPU Open at the address shown here. Thanks for watching, and check out more on GPU Open.